more than a week ago now, we looked at the concept of impulse, which you remember came from Newton's second law. In impulse, you remember the equation ended up being delta P is equal to F times delta T equals M times delta V. It was actually the last two parts of that equation that appear on your data sheet. The point that I want to make here is that impulse came from Newton's second law, F is equal to M times A. 2 days ago, we looked at conservation of momentum, which came from Newton's third law. Remember, Newton's third law says if F12 is going to be equal to negative F21. In other words, if object A applies a force on object B, B will apply an equal and opposite force on object A. Now, the way that manifests itself into an equation that's tailored in terms of momentum is this. We say Pi is equal to Pf. The total initial momentum is equal to the total final momentum if we have an isolated system. And what do we define an isolated system as? It's a system in which we have, somebody said it, in which we have no external forces. There's no outside forces acting to add momentum or to take momentum away. And because of that, what we usually end up doing is analyzing an interaction, either a collision or an explosion, immediately before or immediately after the interaction takes place. The reason we do that is to keep it an isolated system. We're analyzing a car crash, two cars collide, they head off as one object. Okay, it's not going to be very long before friction causes them to stop. If we look at the velocity 10 seconds after the collision has taken place, then friction, the external force of friction, has had a chance to matter. If we look at the interaction just after it takes place, then friction hasn't had a chance to really make any difference. So we'd say that in that case we'd have an isolated system, and momentum would hold. If we looked at it 10 seconds after, momentum wouldn't be conserved. Conservation of momentum wouldn't work because of that external force. So in an isolated system, momentum is conserved. And again, that comes from Newton's third law, where we say F12 is equal to negative F21. Now, I want to focus on this one a little bit more because this is the one that we're working on right now. Pi will be equal to M1V1I plus whatever, however many objects you have. M2V2I plus M3V3I plus M67V67I if you have 67 objects, right? There's a term for each object, an MV times however many objects you happen to have. Remember to add them together. Every once in a while I get somebody saying M1V1I times M2V2I times M3V3I and so on. Remember, it's the sum, right? You're adding the momentum together. PF, same deal. We're going to have an MV term for every object that we happen to have. A lot of times these two objects collide and stick together, so it becomes only one term for one object. But if they bounce apart, then two terms for two objects or three terms for three objects, whatever the case may be. At this point, plug in your numbers and solve. Okay, once you get to this point, except for the signs, positives and negatives, it's actually pretty easy. Remember I told you about that written response test that you're going to have in a couple of weeks here? Well, not in a couple of weeks, but several weeks down the road. And I said, when you're going to use impulse on that test. And remember I said that you got to be careful that you're analyzing one of the objects when you're using impulse on that test. You got to be careful about signs as well. You're also going to get conservation of momentum on that test. And one of the directions is going to be, I think it's north, and one of them south. And when you're plugging those numbers into this equation, M1V1I plus M2V2I, make sure you make south negative. Okay, some people won't do that, and some people are going to get the wrong answer because of that. All right, we were working on some questions here on Monday, where we introduced this stuff. Questions were on page 478. And I assigned them for homework. I asked you to finish them up for today. I'd like to go over at least one of these two questions. Preference as to which one to go over, or do you want to go over both of them here? Two? Okay, two. Anybody need number one, or are we okay with that one? Okay, number two it is. 2 says a 9,500 kilogram rail flat car moving forward at 0.7 meters per second strikes a stationary 18,000 kilogram box car, causing it to move at 0.42. What will be the velocity of the flat car immediately after the collision if they fail to connect? Now, do they really have to tell me that they fail to connect? If they don't tell me that they connect and stick together, then we assume that they don't connect. Got it? Okay, they have to tell me that they do connect. Okay, that's great that they tell me that they don't connect. They're reminding me that there's two objects after the collision takes place. But if they didn't tell me that, I could still solve this problem because that would be my assumption anyways. What do we get for objects here? Two of them, right? Rail car and box car. Let's write down some givens here. Let's say M1 is 9,500 kilograms. Let's say M2 is 18,000 kilograms. Something is 0.70 meters per second. Katie, 0.70 meters per second. Is that V1 or is that V2? Okay, V1, is that V1I or V1F? V1I. Tell me V1I and I'm going to write it down as V1F. V1I, good. Okay, what's the next one? You got another one that's 0.42 meters per second. It's slower. We would probably expect it to be slower, right? Because it's quite a bit heavier. Is that going to be V1 or V2? V2? V2I or V2F? Yes. Yeah. No, it is. Yeah, you're right. It's V2F. Good. It's the final velocity of the boxcar after it's hit, right? Is there anything else that we have here if we read between the lines? We're looking for the velocity of the flat car, right? So we're looking for V1F, V1F, the velocity of the flat car. Anything else here, Fraser? Sorry? V2I, yeah, the velocity of the box car before the collision is 0 because it's stationary, right? Once you get the givens written down, these questions aren't really that bad. It's just getting the givens written down properly because there's so many different, look, there's 2 M's and 4 V's and subscripts all over the place. Keep those straight in your set. All right, so we say PI equals PF. Now, could we do impulse with this? Is it possible to analyze this using impulse? Yes. Yes. How is it possible to analyze this using a concept that says we have a change in momentum, but at the same time possible to use a concept that says the momentum stays the same? How can both of them work and give us the right answer? Yep. What's it? Good. If you're analyzing this problem using impulse, you have to pick a single object, mass 1 or mass 2. Okay? If you're analyzing the object using conservation of momentum like we are, then we're doing the whole thing, both of the objects. All right, so let's say M1 V1I plus M2 V2I, because we have 2 objects, equals, how many do we have afterwards? No one, how many do we have afterwards here? 0? These two objects hit each other and then they just obliterate each other? Is it like, it's like matter? You ever read the book Angels and Demons? It's like matter and antimatter colliding and annihilating each other. That's what we got here, a matter train and an antimatter train. Complete annihilation. How many objects do we get afterwards? Ollie? Yeah, 2 objects. So we're going to have an M1 V1F plus M2 V2F. 2 objects, 2 terms. Got it, Nolan? Can we cancel out anything here? Masses or velocities? Sorry? Okay, yeah, we could get rid of this. That's not a canceling thing. It's just disappearing because value is 0. Could we cancel anything out of each term here? No, Peter? Is it ever possible, do you think, to cancel something out of this equation? Yeah, so if, let's say the train cars weighed the same. So if M1 was the same value as M2, then yeah, you could cancel that mass out, right? Here it's not the case. M1, 9,500 kilograms times V1I is 0.70. So we got 9,500 again times V1F plus 18,000 times V2F. Okay, let's do this on the calculator here. Say 9,500 times 0.7. That's the left-hand side. What am I going to do here? Subtract. See what I'm doing? 18,000 times 0.42. See what I did there? I got to get this term right here over to the left side by subtracting, right? Because it's added to the right side. So I get a value of negative 910. Let's divide that by 9,500. And we get a value of negative 0.096, which is the answer they give us in the book here. So what are they telling us here? First of all, it's not going very fast after the collision. Second of all, first train hits the second train, and then the first train bounces back a little bit, right? That happens sometimes, right? Okay. Playing football, and small guy runs up against the big guy. What happens? Big guy goes back a little bit, but the small guy bounces off him. He goes backwards, right? Right? How many people got that? Okay, not bad, not bad. Okay, we're gonna do question 9.8 here on page 479. It's an appropriately themed question after the last what's it been here now? The last week and a half. Stampeders beating the Eskimos twice. Anybody an Eskimos fan here, by the way? That's good. 110 kilogram Stampeders football fullback moving east at 1.8 on a snowy playing field is struck by an Eskimos defensive lineman moving west at 1.5. The fullback bounces west at 0.25. What's the velocity of the Eskimos defensive lineman just after impact? Collision, clearly collision, conservation of momentum, right? Unless we analyze one of those guys where we could use impulse, but that's not what I'm going to suggest to you. Before we do anything else at least, I'm going to pull out the red pen, circle something. What do you think I should circle? East and west, yeah. This guy's going east, this guy's going west, west. Okay, it reminds us that there's some positives and negatives in here. Something's got to be positive, something's got to be negative. Probably east positive, probably. We're going to make the Stampeders player 1. We're going to make the Eskimos player 2. That means that mass 1 is 110 kilograms, and mass 2 is 140 kilograms. 1.80 meters per second. What is that? What's that going to be? Mika, is that V1 or V2? Object number 1 or object number 2? I said that? Thanks, Mika. That's okay. It's okay. No, it's okay. It's okay. You make your other look. Now we're going to call on her for the next one here. It is V1. Christian, you're right. V1. And is it V1I or V1F? Yeah, good. The initial velocity of the first football player. Good. All right, we got another one here. 1.5 meters per second. V1I or V1F? Kale, V1I or V1F? Sorry, V1 or V2, I should say. It's V2. V2I or V2F? Good. Good. What else we got here? The fullback, which is the first player, bounces back west at 0.25. We're going to make that V1F. Right? The first guy afterwards bounces back at 0.250. And we want to find the velocity of the defensive lineman, the Eskimos player, V2F. Okay, I've got the important part set up. Unfortunately, I've made a mistake or two here. Isaac? Where? V1F, and what? Yeah, V2I. Those are negative because they're to the west, right? Good. We remember that partially, at least, because we have them circled in red. It helps us to remember them, right? PI equals PF, two objects before. And then we get two objects afterwards. Mass 1 is 110 kilograms. V1I is 1.8. Mass 2 is 140. V2I is negative 1.5. Uh, 110 times negative 0.25. There we go. Guys, this isn't any different than the last 3 or 4 questions that we've done, except that there's more terms here. Let's get the left side. Say 110 times 1.8 equals, I'm going to add to that brackets 140 times negative 1.5. That's the left side. Now let's add to that 110 times 0.25. Add it because it's negative on the right side. And then let's divide that by 140. 0.111. It's not different. It's not harder than any of the other questions we've done. It's just more terms, so a little bit more mathematical work. I want you to see by now that these are all the same question. Okay, whether we're talking about the guy picking up the backpack the other day, or whether we're talking about 2 football players hitting each other, they're the same question. Hey, there's a good chance on a unit test or an exam that you're going to see some completely new context to this, but it's still going to boil down to the same thing. Peter? Yeah. Let's have a look at these questions on page 479, please. Okay, let's have a look at number 2 here. It says 125 kilogram bighorn ram butts heads with a younger 122 kilogram ram during mating season. The older ram is rushing north at 8.5 immediately before the collision. Immediately before. Why do they tell us immediately before? Yep. Yeah. Yeah. We want to make sure. I mean, look, guys, sometimes, the word immediately is not directly associated with conservation momentum, right? But sometimes we see something and it's like, it leads us somewhere, right? If a question talks about there being no external forces, well, or the question says it's an isolated system, or the question says immediately before, then what they're likely doing is guiding us into a conservation momentum thing, right? It doesn't always say that. It's not. We don't always get those little hints, but sometimes we do. Okay, we know this is going to be conservation momentum. No external forces. It's an isolated system. It's not the only thing you can do with an isolated system, but realistically, that's where they're leading us. The younger ram moves at 0.22 afterwards. What's the velocity just before impact? All right, let's say the heavy one is number 1. The light one is number 2. I'm going to say M1 is 125. I'm going to say M2 is 122. The older one is the heavier one. So we're going to say V1I is 8.50 meters per second. We're going to say V1F is negative 0.11 meters per second. Probably should have circled that in red to remind us that we got a negative there. We're going to say V2I is what? The 122. Yeah, we're looking for a V2I. we're going to say V2F is 0.22 meters per second because it's going to the north after the collision takes place. So stick with the last question we did. We'll say PI equals PF, and we'll say we have two objects before and two objects after. So we have two terms, M1 V1 plus M2 V2. 125 times V1I is 8.5. 122 times V2I, is that what we're looking for? 125 times negative 0.11. V2F is 0.22. Well, you can see how easy it would be to make a mistake on this with the wrong sign, right? See how easy it is to make a mistake with the signs, because there's so many different things. So easy to miss a negative here. All right. Let's say 125 times 8.5. Actually, you know what? I'm going to do the right side first here. The right side first because it doesn't have the variable that we're looking to solve for. So let's do that right side first. 125 times negative 0.11 plus equals, let's add to that with some brackets, 122 times 0.22. Here's the right-hand side. Now let's subtract from that 125 times 8.5. And then let's divide that by 122. Negative 8.6. And what does that negative mean? Yeah, it means to the south. So 8.6 to the south or negative 8.6. How many people got that? Good. I was going to say we'll have a quiz on this on Friday, but we could probably go tomorrow. Want to do tomorrow? Get it over with? Let's do another one here before we give you the quiz, before we decide. And we'll see here. So it says a 75 kilogram hunter in a stationary kayak throws a 0.72 kilogram harpoon at 12 meters per second to the right. The mass of the kayak is 10 kilograms. What will be the velocity of the kayak and hunter immediately after the harpoon is released? What do we got here? This is not a collision, but it's still conservation of momentum, because the total momentum before still equals the total momentum after. It's always the case as long as we can isolate the system. It's a little bit different though, because before this interaction takes place, nothing's happening. Like nothing's hitting each other. After it takes place, we have a harpoon going one way and a hunter going the other way, a hunter kayak going the other way. This is like a bomb exploding, right? This is an explosion where one object becomes two. The hunter kayak harpoon becomes the hunter kayak and the harpoon. Throw a ball goes one way, you go the other way. Throw a harpoon goes one way, you and your kayak go the other way. Bomb explodes, one piece goes this way, one piece goes that way. Yep. Yeah, that's exactly what it is. So it does some givens here. I'm going to say M1 is going to be, what do you want to make M1? Ollie? Yes, good. 85 kilograms. Because the hunter and the kayak don't split up ever, right? They stay together the whole time. So we're going to make their mass the one total of 85 kilograms and leave it that way through the whole question. M1 is 85 kilograms. We're going to make M2 0.72 kilograms. Now, before this interaction takes place, there's one object, right? What is the velocity of this one object, the hunter, harpoon, kayak combo? 0. VI is 0. I'm not going to call that V1I, V2I, it's just VI. It's 0. Afterwards, the harpoon goes at 12 meters per second. We're going to say that's V2F, 12 meters per second. And we're looking for the velocity of V1F. That's going to be the hunter/kayak combo. Prediction here. How fast is that hunter/kayak combo going to go? 12 meters per second? More than 12 or less than 12? Why? Yeah. Yeah, so the harpoon goes one way with a certain momentum. The hunter and the kayak goes the other way with the same momentum. But since the hunter and the kayak have much more mass and they have the same momentum, the velocity is going to be quite a bit smaller, right? So let's figure that out now. Let's say PI equals PF. I'll tell you what, I'm just going to write in 0 for PI. I mean, I could write in MVI, but we know that the term is 0. So if everything before the collision or explosion is at rest, just make it 0. M1 V1F plus M2 V2F. 85 times V1F is what we're looking for, plus 0.72. Boy, it's going to be a lot smaller velocity, right? Because it's a much bigger mass. V2F is 12 meters per second. So let's figure this one out on the calculator. 0.72. Actually, let's say negative 0.72 times 12. Why did I do that? Why did I make it negative? Yeah, I got to pull it to the left side. Do that by subtracting. Let's divide that by 85. Negative 0.101. So the harpoon goes forward at 12. The hunter and the kayak go backwards at 0.1. Is that reasonable? Yeah, it's a much smaller velocity, but it's because it's a much bigger mass. All right. All right. Here's a couple more for you. Page 475. Let's have a look at question number 1, everyone. This one says 110 kilogram astronaut and a 4,000 kilogram spacecraft are attached by a tethering cable. Both masses are motionless relative to an observer a slight distance away. The astronaut wants to return to the spacecraft, so he pulls on the cable until its velocity changes to 0.8 meters per second toward the spacecraft. What's the change in velocity of the spacecraft? We're going to say M1 is the astronaut, 110 kilograms. M2 is the spacecraft. We're going to say that V initial is 0. We're going to say V1F is 0.80 meters per second. And we're looking for the change in velocity, but really, since it was initially 0, we're looking for the final velocity of the spacecraft, right? I think it's going to be bigger or smaller than 0.8? Smaller, because it's heavier, right? So let's say PI equals PF. Let's say M1, V1, actually, let's just say 0 initial momentum. 0 because it's all at rest, right? Equals M1, V1F plus M2, V2F. So, Christian, we're going to take this over by subtracting. Multiply those together, take them over by subtracting. That's going to give you negative something. And then you're going to divide that by 400. Make sense?